I was asked to give a lecture on my research, and I have chosen this topic, which is a recent development of something I have worked on for 30 years. It started in 1983 when my wife gave me a paper by Clive Ranger, and she had the feeling that it needed a statistician to develop the theory. That is now 30 years ago, and we have developed the theory. One of the things that has happened then is the fractional processes, which is a very big topic, and I will explain that in more detail. Could I have the first slide, please? It is joint work with Morten Nielsen, who is a professor at Queen's University in Canada. So here is what I want to do. I have two examples of situations where the fractional model is a useful model. Then I'll tell you the basic concepts and the motivation, and then we go into the technicalities. The gradient representation theorem is the core result in this part of the theory, and I'll explain to you why that is. The most important contribution, in a sense, is a discussion of conditional inference. We always condition on initial values, but for fractional processes, you have an infinite past, and that makes it very difficult. We should have the solution in terms of asymptotic inference, and then some conclusions. The topic is quite technical, and that, of course, is not possible in half an hour, so I'll be skipping. You should think of this as an introduction to the topic, and the main message is that it is pretty clear what you should do all the time, but it's also pretty clear that doing it is very difficult. But at least we know the structure of the problem. So this is the first result, the first application. It is a variable which in finance is important, that is the log of the volatility, the realized volatility. It is daily observations, 1,366. And what I have on the left-hand side here is the autocorrelation function. When you have a time series, you always try to measure how much glue or how much dependence is in the time series, and you do that by the autocorrelation function. And the most important number here is this one, which you may not be able to read, but it's 100, and it says even after 100 days, you still have a serious amount of correlation. So it's not a question of the last day or the last 2 days, but after 100 days, you still have a lot of autocorrelation. A very nice plot is the right-hand side, where if you go through the theory, you can show that there's a certain stochastic process that I'll come to. If you work out the variance of the sum, the so-called long-run variance, and take the logarithm, it should depend linearly on the lag length h. And that means if you have these, sorry, could you go back please? And if you go, if you take the log h and plot it here, and the log realized log variable there in this direction, if this is a linear relation in h, then it's a sign that you have a fractional process with, and you can read off the coefficient d, the fractionality, simply by looking at the slope of this line. So this is a very convincing example that the usual type of autoregressive models, where the autocorrelation function goes to 0 exponentially, that would come up like a curve over here. And it's certainly not a curve, and that means that this cannot be described by an autoregressive with a few lags. You need infinitely many lags. You need what they call long-range dependence. And you can see this is exactly long range